Welcome to The Explainer. Today we're going to dig into a really cool mystery, one that's probably sitting right there in your science textbook. We all get that electricity can give us light and heat, right? But what if I told you it could also push things, an invisible push? So, let's go ahead and investigate this.
Just picture this for a second. You pass an electric current through a wire, and instead of just warming up, it suddenly jumps to the side. I know, it sounds like something out of a sci-fi movie, but this very idea is what powers so much of our modern world. So, how on earth does it work?
For this explainer, we're basically going to become detectives. We'll set up a key experiment, hunt for clues, and by the end, we're going to crack the code behind this invisible force. We're going to figure out the exact rules that make this strange and powerful effect happen.
Okay, so our investigation starts with setting up the experiment, just like you find it in Activity 12.7 in your textbook. We just need three main things.
So here's our setup. First, we've got this small aluminum rod, just hanging there so it's free to move. Second, we bring in a strong horseshoe magnet and place it so the rod is sitting right between the north and south poles. This gives us a powerful magnetic field. And finally, we hook up a battery to send a current flowing through that rod. So, what do you think is going to happen when we connect that final wire?
And there you have it. The second the current starts to flow, the rod gets a push to the side. It actually moves. This right here is our first absolutely crucial clue. If you put a wire with a current inside a magnetic field, it experiences a force, an invisible push.
Okay, so we've confirmed there's a force. Now, any good detective knows the next step is to start changing things up to see what happens. Let's start messing with our setup a little bit and look for more clues.
The first and most obvious thing to try is reversing the flow of electricity. If the force and the current are connected, then changing one should have some effect on the other, right? Let's see.
And check this out. It works exactly like that. When the current goes one way, let's say from B to A, the rod gets pushed to the left. But then if we flip the connections on the battery so the current flows from A to B, the rod gets pushed to the right. So the direction of the push is completely tied to the direction of the current.
All right, let's recap what our detective work has turned up. 1. There is definitely a force. 2. If you reverse the current, you reverse the force. And 3, and this is something other experiments show, if you flip the magnet over to reverse the magnetic field, the force also reverses. So here's the big takeaway. The direction of the push depends on both the direction of the current and the direction of the magnetic field.
Okay, we have our clues. We've got a force that depends on two different directions, the current and the magnetic field. Now that might sound a little complicated, but lucky for us, there's a really, really simple way to figure out exactly which way that push is going to go. This rule is just so elegant, it's easy to remember, and it's basically the key that unlocks this whole thing. It's called Fleming's left-hand rule.
So here's how it works. You take your left hand and you stretch out your thumb, your forefinger, and your middle finger so they're all pointing at right angles to each other, kind of like a 3D axis. Each one of those is going to represent one of our key players, the field, the current, and that resulting force.
Now this is the really cool part. Your forefinger, that points in the direction of the magnetic field. Your middle finger points in the direction of the current. And if you get those two lined up correctly with your experiment, your thumb will automatically point in the direction of the force or the motion. It's this perfect little predictive tool that you literally carry around with you all day.
So we can predict the direction of the push. That's a huge step. But what about its strength? How could we get that rod to move with even more oomph?
This is the next logical question, right? It's one thing to know a force exists, but in the real world, we need to control it, make it stronger or weaker. So how do we get that little aluminum rod to jump even further? Well, the experiments give us three really clear answers. First, if you crank up the current flowing through the rod, you get a stronger force. Simple enough. Second, use a beefier magnet to increase the magnetic field strength, then, the force gets stronger. And third, if you have a longer piece of the rod inside that magnetic field, you guessed it, the force increases. More current, a stronger field, more length, you get more push. So now we get the rules, we know how to control the force, but why is any of this important? Well, it turns out this invisible push is way more than just a neat science experiment. It's actually one of the most fundamental principles behind all of our modern technology. Seriously, from the moment your alarm clock goes off to when you turn off the lights at night, you are constantly surrounded by devices that depend on this very effect. It's like the hidden engine of our world. Just think about it for a second. Your fan, a blender, an electric car, a washing machine. If it spins, it probably has an electric motor inside.
And every single one of those motors is just using electricity and magnetism to create this exact force over and over again to make something turn.
It's also how you hear your favorite music. A loudspeaker takes an electric signal, the current, and runs it through a coil that's attached to a cone. That coil sits in a magnetic field, and the force pushes and pulls the cone back and forth, creating the sound waves that hit your eardrums.
But the applications get even wilder and go right inside our own bodies. Your textbook actually points out that the nerve signals firing in your brain and body are basically tiny little electrical currents. And just like that wire in our experiment, these tiny currents create their own tiny magnetic fields.
And this amazing link between our body's own electricity and magnetism is the whole idea behind incredible tech like MRI scans. Doctors can actually use these tiny fields to create stunningly detailed pictures of our organs. All of that thanks to the very same principle that pushed that little aluminum rod in the lab. So we've seen how this incredible link between electricity and magnetism creates the force that runs our motors and even lets us see inside the human body. But this relationship is about more than just making things move. It's also at the very heart of the safety systems built into your home's electrical wiring. How does that work? Well, that's a story for next time.